So why are we here?
Well, it all started with a press release regarding the successful attack on the system we discussed, and yeah, you see some of the reactions.
Yeah, and it was sometimes dramatic discussions with the journalists. It was a rather unusual situation for us because we had to explain the cryptographic research to non-specialists, and of course it happens that some misunderstandings occurred, and of course it's a complicated topic. So we read, for example, articles like this. Somebody takes out his remote control and all cars on the parking start blinking funnily. So this is the result of our conversation, probably our fault.
Yeah, and we thought that the Chaos Communication Congress here in Berlin might be a good platform to clarify some of the things that have been written there, and to show you what an attacker really can do and what he cannot do. So to do this, we'll start with a short general presentation how remote keyless entry systems work, before we then take a closer look at the keylog crypto system, which we actually took a closer look at, and we'll present some of the successful attacks on the keylog system. And finally, we'll show what, and actually perform live, what an attacker can do with the attacks that we explained earlier. So, but let's start with a look at remote keyless entry systems. Once upon a time, people were annoyed by using mechanical keys. So they said they want to just press a button of a remote control to unlock some kind of device. And yeah, what you basically have is one transmitter. You press a button. With the first systems, a unique message was sent and the system unlocked. In the first cases, as I said, it's basically like a password. The code that was sent was always the same code. Some of these systems are actually still in use. The problem, of course, is anybody who is able to eavesdrop a message and to record a message will also be able to resend this message, and the system cannot distinguish between the right remote control and an attacker. So basically, someone else can also enter such a system. So this is called a replay attack. Of course, industry reacted to this rather quickly, actually, and came up with something called rolling codes. What basically changed is that both sides were equipped with a counter that is increased each time a message is sent. So by this, the message that's being sent is a unique message each time you press the button. And to make this message, to stop eavesdroppers from recovering the counter value, this message is actually encrypted, typically using some kind of block cipher. And yeah, together with this encryption and the counter value that is increased every time you are able to stop replay attacks. There's an alternative system, it's called the challenge response system. Here actually the secured device sends some kind of challenge, a number, and the remote control calculates a response, again using a block cipher and using some secret that only those two parties know. And yeah, the car then checks the response on the secured system, and yeah, if the response is correct, it will unlock. And there are a few disadvantages to this system. In this case, it's rather practical disadvantages. Both sides need to be able to send and to receive messages. So the systems are more expensive to build and also more complicated to build. In the scenario before, we just had one sender and one receiver. That's much easier to build. So for many systems, this is not so interesting because it's more expensive. Yeah, now we're taking a look at the keylog cipher. That's cipher we focused on. And it's being used for both of these systems. It's for active systems, usually the rolling code scheme is used, while for like in garage doors or car opening systems or access control for building. On the other hand, the passive systems are usually used in RFIDs, which you can, for example, find in car immobilizers. And when you look at Wikipedia, you'll find a list of car manufacturers which supposedly use keylog. Actually, this list is neither complete nor is it correct. So do not trust them too much here. We know that some car manufacturers actually use keylog, but well, their keylog is not really a market leader. This is different for garage doors. There, basically every garage door system using encryption is using keylog, so they are market leader. So that's why we took a closer look at them, and we were wondering how secure is this system.
Yeah, and to put you in the picture how such a system works, so we went in the hardware store and we bought you a garage door opener system. Part of it, the garage door, is in this bag here, and the garage door system consists of this receiver. This is exactly what is installed in your garage, and then it's connected to the motor that controls the door. And then instead of the garage door, because Thomas said it was too heavy, we took this little red light here. It also can remind us of all the car alarms where keylog is used. And yeah, I plug it in here. So now it's sharp, and we've got the remote control here. And some magic is going on. Every time I press on this button here, then this light is flashing. And it's up to your imagination now to see the garage door swing open and close each time when you see this light. So it looks like a little bit like magic. Let's have a look at the details of what is going on when we press on this button. So each time we press the button, there's this counter. It is increased by 1 inside this transmitter. And then the plaintext furthermore consists of some constant discrimination value and a function that is just indicating which of the buttons of the remote control is pressed. So if you have several garages or whatever, then this plaintext is encrypted with keylog, and the result is the hopping code, and it's then sent to the side of the transmitter, to the receiver. And the receiver then first decrypts the code and checks whether this discrimination value is correct, whether it's the same discrimination value. So it's very likely that it's a valid hopping code, and then it checks the counter value if this counter value is newer than the one previously stored in the receiver. So then it knows it's a valid new hopping code, it opens the door, or if it's an old one, it decides, no, I won't open the door, I do nothing. And so what is important to mention here, that in every message, there's also transmitted the serial number, not encrypted. So this means every attacker knows the serial number. This might be important during the talk. Yeah, we have this device key here. Where does it come from? It works like this. If you are a manufacturer of garage doors, for example, then you get one manufacturer key assigned. And this manufacturer key is then in all your products, and all your receivers with the same manufacturer key. And when there's a newborn transmitter, freshly newborn in the factory, it obtains a unique serial number, and then according to the serial number, with the manufacturer key, there is this device key. For each transmitter, there's a device key derived in the factory and then programmed into this transmitter. So it's in the secure environment, so it's no problem to directly program the key into it. This changes when we have a look at the receiver. How does the receiver get known to the secret key of this transmitter? Obviously, we do not want to send a secret key in clear because it's a secret key. We don't want to send something secret in clear. How it works is the transmitter sends its serial number, sends it to the receiver, and the receiver has got this manufacturer key burned into its secret memory. It's sometimes stored usually it's a big microcontroller running in the receiver, and it's stored in the secret memory, and then this receiver can do exactly the same key derivation that happens in the factory. So transmitter sends the serial number, and the receiver can do the key derivation. Then it knows the key of this transmitter, and it stores it together with the serial number. The next time we can use it, press a button, and it will open the garage. Okay. I said that there is a key derivation function used here. There's two different schemes proposed by Microchip. On the left side, you see the weak key derivation with an XOR. So you see the input is the serial number, then there is two very simple functions. This is usually padding with a constant value or with zeros. It's not so important. Then it's concatenated to make the same length with the manufacturer key, and then we have an XOR here, and the outcome of the XOR is the device key. And here is the secure key derivation scheme, where a keylock decryption is used with the manufacturer key to produce the device key. And yeah, from the attacker's point of view, this is trivial, because if you have one device key and you have the serial number, it's easy to inverse the XOR operation to get the manufacturer key. The inverse of an XOR is just, again, an XOR operation. Here on the secure key derivation, it's still very difficult, because even if you have many device keys and if you have a lot of serial numbers, you still have to break keylock in order to get known to this valuable manufacturer key. So now everyone should have at least a basic understanding of how these remote control systems work.
So we take a short look at the history of the keylock cipher. Actually, it was invented in the mid-80s in South Africa, back during apartheid. They had some export restrictions, so they had their own little crypto community. And there the cipher was developed, and shortly after the end of apartheid, it was sold to an American company called Microchip, which then started to build remote keyless entry systems around it. And well, they were actually adopted quite well and used by many other manufacturers. And during the whole time, the cipher was never really published, so it was not publicly known. Only the people who built implementations of it had access to those systems, to the description of the cipher. And yeah, basically it was never really reviewed by a huge crypto community. This changed actually in 2006, when the description of the cipher suddenly appeared on the internet, on some Russian hacker website. And by then it only took the crypto community about 1 year to develop first attacks. First attack was developed by Andrei Bogdanov, who's also a member of our group in Bochum. And yeah, some improvements and stronger attacks followed closely afterwards. These attacks are all mathematical attacks. And the strongest of these attacks actually just needs 2 to the 16, so roughly 65,000 plaintext ciphertext pairs, and about 50 PCs doing calculations for about 10 to 14 days. And then we are finally able to recover a device key, which from a mathematical point of view, this is as broken as a cipher can be. So nobody would even consider keylock for hard disk encryption anymore or longer communications. But for this very specific scenario, where you usually do not send very many messages of remote keyless entry systems, it still looks a little bit different. Especially in the rolling code case, because in the rolling code case, you never see the plaintext, you never really see the counter. As an attacker, we never see the counter value. So we do not, the conditions for the attack are not really fulfilled. And what's even more important, we would like not only to recover the device key, but also the manufacturer key. And as Timo just showed, the device key only allows us in one very specific case to recover the manufacturer key, and that's the case when the XOR key derivation is used, and if we are using a challenge response system, which is also not very common. So in these cases, we are able to use mathematical attacks, but in all the other cases, they are not very applicable. So we're sitting in our lab and we're thinking, can't we do anything better using physical attacks? And yeah, well, it took us a little while, and then we also came up with some physical attacks. The attack we use is a so-called power analysis attack. And what we have right now is the transmitter you just saw. Sorry. And what we do is we know that the encryption, keylock encryption is being performed inside, and we want to recover the secret key. And yeah, basically we know the cipher, we also know the hopping codes, and now we record the we record the power consumption while the device is actually performing the algorithm, and we record this using an oscilloscope. The recorded data we will then later on pass on to a PC to analyze it and to run the power analysis attack. And if the attack succeeds, we recover the secret key of this one device.
So, and of course, we were not the first ones to invent these power analysis attacks, but it's rather known for quite a long time already. So, in the end of the Second World War, there were already these kind of machines that were used for the teletype encryption machine. They were used for the encryption. It was, of course, very important for the military, and it turns out that the electromagnetic radiation, the emanation of this device, could be seen from another building from the other side of the street, from an opposite building, and one could see the plain text that is encrypted with this machine. So that was, it's already known a long, long time that there exist side channels. This was, and the Tempest project was founded by the US government that investigated how to protect cryptographic devices that they do not leak so much information. You might also have heard that it's very old, that it's possible to see the content of the video screen of them old monitors or TVs that use a beam to produce the pictures before the invention of the TFT or LCD displays. And you could also see the password that is typed in on the screen then from another room, for example, only from the radiation of this beam that draws a picture on the screen. Yeah, so it was only that the secret services and only the intelligence community knew about them. Side channel attacks, a very poor understanding for normal people, until the second half of the 1990s when the golden years of side channel attacks started. So, for example, there was a fault attack on RSA, fault attack that you shoot at the cryptographic device with a laser or with a flash to produce an error and in the output. And if you've got this output with the error, from this you can calculate the secret key of the RSA. That was 1996. Also, Paul Kocher in 1996, he just measured the execution time during the execution of the algorithm accurately, and he could also conclude the full key only from measuring the timing of the full execution. Then we had the first SPA, simple power analysis, in 1998, also by Paul Kocher. This is an example of a microcontroller that does an exponentiation. If you do an exponentiation, you want to square and multiply, and here you see a squaring. It consumes less power than a multiplication, and so by measuring the power consumption, only one trace, you can directly see that a 1 or a 0 is processed, and you can also directly read the key that is used for the exponentiation. Yes, and since this time, there were a lot of research papers, side channel attack research papers, for example, in the CHESS, Cryptographic Hardware and Embedded Systems workshop, very famous. And, but so far, there's no documented case that criminals, for example, used power analysis to break a system. And all the researchers, in doing the research, they usually attack their own implementations, so they know exactly what they're attacking, and they can cheat a little bit by generating, for example, a signal that starts the oscilloscope at an appropriate point in time, and that facilitates the attacks. And we now close this gap by looking at this commercial product, and we knew nothing. When we started the attack, we only had a black box implementation. We knew that the keylog cipher would be somewhere in there, but nothing more. And so now we want to take you through the steps that everyone has, that you would have to undertake in order to power analyze a commercial system. So first of all, you always have to look, what do you want to attack? Analyze the cipher. Yes, there's a question there, please.
Why is it called a side channel?
Do we have a microphone for this guy?
Why is it called a side channel?
The question is called, why is it called a side channel attack? So the answer is because you do not directly, you do not mathematically cryptanalyze the cipher, but you use the side channel of the power to extract the key. It's like someone doing a bank robbery or wants to open a safe in a bank robbery, right? He can use his stethoscope to listen to the sound of the mechanical locks, and then from the side channel of the sound, he can conclude to the right position of the mechanical lock, right? So question is answered, brilliant. So after we know the cipher, we perform some measurements with an oscilloscope, for example, and then we work on these measurements, post-process them, and then we come to the main step, the key recovery.
So let's first look at an analysis of the cipher. So usually if you want to break a device and you know the cipher, you'll just look into the literature and look if someone else already cryptanalyzed the cipher using side channel attacks. In our case, this was not the case. Nobody did look at keylog before, so we had to do it ourselves. So let's take a look at the cipher. This is what the cipher looks like. It has a 64-bit key, which is stored in this lower register, and it has a 32-bit block length, so that means that the plain text is put into this state register in 32-bit chunks, then the encryption runs once, and then in the end you have the cipher text standing here, which you then transmit via the RF interface. And we have the state register is realized as a nonlinear feedback shift register. Nonlinear because we have a nonlinear function here, where 5 taps enter this nonlinear function and are mapped to one output bit. This output bit is XORed with other output bits from the state register and with one key bit, and this is then fed back into the cipher. So this whole thing is clocked 528 times, and then, as I already said, we have the ciphertext which we can transmit via the RF interface. Now what we had to do is we had to come up with a power model, so we can basically predict the power of the device and of the cipher, depending on the key and other things. And for the model we had to make some simplifications. The first simplification is that we ignore the combinational logic part because it's rather small and it consumes rather little power. So we just ignore this middle part, which leaves us with the 2 registers, the key register and the state register. And it's known that the power consumption of registers depends on the number of on the value inside. So generally it depends on the number of toggling zeros and ones in those registers. And we have the key in the lower register, and the key is just being rotated. In each clock cycle, it's just one bit being moved from the left to the right. Actually, the other way around. So basically, the value inside the number of ones or the number of toggles in this register remains constant. So the power consumption of this part is constant. Well, the state register nevertheless changes because of the nonlinear function. The values inside change with each clock cycle, and we can conclude that the variations of the power consumption relate somehow directly to the state register. And now we looked at the feedback function, which you can see here in the equation. So a bit that is fed back at each clock cycle depends on the key, and it depends directly on one key bit. So basically, if we know the state, we can always conclude some information about the key. And this is what we will do later on. So we will analyze the variations of the power consumption to gain information about the key and finally recover the key.
Right, it seems we know everything now about the cipher, so that we can actually proceed with the next step, do the measurements. And for performing the measurements, you can either buy such an oscilloscope as depicted here. A whole digital oscilloscope. It costs you a fortune. It costs you as much as a small car. Or you can just buy one of these USB oscilloscopes. Small, but also very reliable, also very sufficient. You can connect them to the USB port of your PC, and then you connect this probe to the transmitter. You connect it, and then you press on the button several times, and while you press on the button, you measure the power consumption with this thing. All right, it's still blinking. So, for measuring the power consumptions, you have 2 options. Here on the left side, you see some PIC microcontroller here, as used on the receiver side of the garage door, and there is some resistor inserted in series with the device, because you want to measure the power consumption, so you need to modify the printed circuit board here and insert this resistor in series with the device, and then connect the oscilloscope to measure the voltage that drops over the resistor. So this is rather complicated because you have to modify something in the circuit, and it looks rather ugly, and it's difficult to see here. The second approach is that we just measure the electromagnetic field. That's the emanation of the chip while it operates, only the radiation. And here you can see a so-called near-field probe. It's positioned close to the chip that performs the key lock and hardware. And surprisingly, the results from this approach for measuring the field are comparable, almost as effective as the results from this inserting the resistor and measuring the current. And this is the result when we take one of these remote controls and we measure 1 keylock encryption one time pressing this button. This is the result. On the right axis you see the time, on the y axis you see current. So you see the device always consumes between 0.5 and 3 milliamperes. And now some trial and error starts, because you need to guess where does the keylog encryption happen. And the beginning is very easy. You press the button somewhere here, and the device starts to operate. And the end is also easy to see, because that's where the device sends the hopping codes. So the keylog encryption must take place somewhere in between these 2 points. And we first guessed it might happen here, then we guessed there. It turns out, no, this is where the device writes into the EEPROM. How did we find out this? We just cut off the power directly at this point in time. We cut off the power of the remote control and started it again, pressed the button again, and the same hopping code was produced again. So we knew the counter has not increased. This must be the writing into the storing the next counter value. And yes, after some trial and error, I think it took more than 1 week, we found that the keylog is actually right here. So from now on, we are only interested in this time period between 20 and 24 milliseconds, and the rest is not important anymore. Okay, we measure this several times, and what we get is a large amount of data, and it's not very well aligned, so it needs some post-processing. This is the area with the keylog encryption. We've just zoomed into it, and the first problem is now we acquire many traces, and we want them to be aligned exactly, because afterwards we want to process them mathematically. So in the case of this remote, we were very lucky, because there's a special feature here in the trace that allows us for starting the oscilloscope very accurately. This was not so easy for the software implementation on the PIC, but there was a question here first.
How good is the internal clock?
The question was how good the internal clock is, and we will see this now, because it's not so good, because even if you line the traces very, very accurately here at the beginning of the trace, during the encryption, the clock is not so reliable and it's not so stable, and not like some people have got a quartz watch, but it doesn't operate as reliable. And what happens is, if you look at the later point in the traces and zoom in, if you look carefully, there's a blue and a red trace here, and there's always 2 peaks here. You can always see 2 peaks, and they should be on top of each other. That's our wet dream, so that we can analyze it mathematically more easily. And yes, the solution for both compressing the traces, reducing the size of the traces, and at the same time get rid of this so-called clock jitter, when the clock is unreliable, is very easy, called peak extraction. Only take the amplitude of these peaks, and only store the amplitude of these peaks in an array, and forget all the rest. We say all this, not important, no information. We say all the information is only contained in the amplitude of these peaks. Now we have well-aligned data, and we have dramatically reduced the size of this. We come to the most important bit.
Most understandable bit. Yeah, so finally we have all the data gathered, and we want to run the key recovery. We really want to perform the side channel analysis or power analysis attack. And what we now do actually is we take the real power consumption, which we just measured, and we correlate it to the hypothesized power consumption, which we derived from our power model. And the correlation function looks a little bit scary. It's nothing more than just the correlation function with the power we measured and the hypothesized power. And part of the hypothesized power consumption is the key. So we do this. We produce this model for the different key guesses, and we do not have to guess the whole key at once. So it's a 64-bit key. That's more keys than we can try with a brute force attack on a normal PC. So what we do instead is we take a small portion of the key and guess each portion at a time. So what we did actually in this example is we guessed the power consumption after for round 6 of the cipher. So we had to guess 6 key bits. 6 key bits are 64 possible keys we had to guess, and these 64 key guesses are plotted here. The correlation is between the power consumption which we measured and and the power consumption which we hypothesized, and the red line is the correlation for the real, for the right key, while the gray lines are the hypotheses for the wrong keys. And as you can see in round 6, which we hypothesized, we get a correlation of almost 1, while the correlation of the wrong keys is slightly smaller. So we are able to distinguish the right key from the wrong keys. Right now we just got 6 bits of the key, so we have to repeat this again for round 12, for round 18, or for different rounds we can repeat this attack, and we will finally recover the whole key. Yeah, and for everybody who thinks this was a little bit too quick, we also want to offer a DPA workshop here at the Chaos Communication Congress, and then you will be able to learn how to perform such an attack. And yeah, we will offer 2 things. First is measuring the keylog transmitter, like you find inside of this, and we'll also bring a smart card with an AES where you can take a look at. And yeah, well, for further information, please keep updated on this web address. Unfortunately, it's not really filled yet, but we'll do that.
We brought all the equipment,
yeah.
and we will start working on it tomorrow morning, in the morning. And we put you some traces there, and then everyone can have a go and try if he's successful. And
Yeah, with our help.
yeah, that's the workshop. Hope to see many of you there. That was the advertisement.
Mm-hmm. So now all we did up to now was only concerning the transmitter. Now we are actually going to take a closer look at the receiver. And why do we want to look at the receiver? Because actually here, like Timo said before, the key derivation is performed, and yes, we still want to get to the manufacturer key. Up to now we just got the device key. So we basically do the same procedure we did over there to this device, to the receiver. We will measure the power consumption, but this time we measure it while the key derivation is being performed. We measure it again with an oscilloscope. We pass the measurements to a PC to run the attack. If we are lucky, we end up with a manufacturer key. And if we have the manufacturer key, we can produce a new remote, can produce another remote, can produce many remotes.
Very valuable, very useful, this manufacturer key. So the results look as follows. So if we take such a transmitter like this, it takes, in the best case, 5 times pressing the button and computation in the order of minutes to get the 64-bit secret key out of the device. So what you see here is on the right axis the number of traces that are required, and on the y-axis the correlation coefficient that Thomas just explained. And when this line goes up, it means key found. Right? So this is in a good case, and it's not fair, but you might want to compare this to the 50 Pentiums and 2 weeks mathematical cryptanalysis to extract one device key. I think this is the proof that implementation attacks, such attacks are very efficient and dramatically outperform these mathematical attacks. Attacking the receiver, that is getting the manufacturer key out of the software, was a little bit more complicated because the alignment was more difficult and the software behaved in some way funny, so the correlation wasn't as good, so we needed 5,000 traces approximately and computation time in the order of hours. But still, it's worth the effort because afterwards you have got the manufacturer key and can do a lot of things with it. We also had a look, at different packages. On the left side you see the old-fashioned DIP package. You see it's easier to attack than the SOIC package with the new low-power technology on the right side. It's because if it's a low-power technology and you want to measure the power consumption, low power means less signal for you, more noise, and so you need some more traces. Yes, furthermore, what kind of equipment do you need to perform such a power analysis? You see on the right axis the sampling rate of the oscilloscope. This behaves somewhat linear to the price. So if you want an oscilloscope with a high sampling rate, it's more expensive. And on the y-axis, you see the number of needed traces for a full key recovery, and you can see that it's already sufficient to have an oscilloscope with a sampling rate of less than 100 megasamples per second, which is really cheap. You can get it for less than 200 euro or something. Could be worth buying. And we had all these results, and of course we are responsible researchers, and we did not go at once to the press and to the 25C3 and say, hello, this is a weak cipher and so on, but first of all, we of course wrote everything down and sent it to Microchip, the US-based company that produces this system. And we explained them about the attacks, we explained them about the implications and what one might do. And first they did not answer at all, and after several times asking and asking again, they said, okay, we are not interested, and your attacks are not practical. Okay, so we went out and published it because we thought it's interesting for all those customers who believe that they've got some very secure system, and they've got the right to know how secure it really is, right? And then there came this camera team from Nano, and we opened the garage in front of the cameras, and then these guys from Nano, they went again to Microchip and asked them again about their cipher, and this is the outcome. The outcome is, first of all, that Microchip still believes that keylog is one of the most complex and most secure encryption systems. So those of you who have listened to the mathematical part of this talk might have learned more than those guys. And more importantly, under realistic and practical assumptions, an attack is not possible. Okay, we just leave it as it is, because we come now to the practical part of the talk, and afterwards everyone can make up his own mind about the relevance or practicability of the attacks.
Timo? You wanted to say something about that?
Oh yeah, this is, by the way, this is the view out of our laboratory. This is the beautiful Ruhrpott area in Bochum. The rainbow is always there, of course. And it's definitely worth... yeah. It's also interesting that Thomas will now open the folder with the live demo that usually works.
First, I will shortly demonstrate or show you what else we brought with us. We went to the local hardware store and we bought a keylog system consisting of one receiver that you usually connect to your garage door, engine, or something like that. And we manipulated it, so we connected it to the parallel port of our PC.
So basically we only use it for receiving the data, right?
Right, so the PC is finally also able to read the messages, and then the PC is also connected to a transmitter, also via the parallel port, and can also send messages to a garage door.
And then the rest happens in software, so this is nothing cryptographic, it's just everyone who can use a soldering iron can connect this device, any device from the hardware store to your parallel port. And the cost is say 50 euro for the system here with the receiver, and then 3 euros for this battery. So 53 euros approximately. This is everything you need. Yeah.
All right.
Yeah, there's the software coming with it.
This is the software side, yeah?
It's not yet available on the internet. So.
Shall we shortly, we will demonstrate it quickly,
Yeah,
right?
I think, yeah.
All right.
I press it, so what the software can do is it can intercept hopping codes, right? Let's intercept some more hopping codes maybe. Yeah, so each time I open the button, the software now puts down the codes over there. Maybe a third one, no?
Yeah, that's true.
Because I'm so happy that it's working actually.
Yeah.
Oh, it's
Finally
really
it's working.
So, yes, if you have a close look, some of you, the clever ones, might have noticed that this field has already been filled out. Why? Because the serial number is contained in this hopping code over there. You see on the right side, it's always the same zeros and ones that are sent over the RF interface. So this is the part with the serial number, and on the left side is the ciphertext. And yeah, maybe you can try to decrypt the ciphertext. No?
We don't have a key. I don't think this is going to work.
Oh, where do we get the key from?
Didn't we talk about some kind of side channel attack before? So that basically takes us to the implications part. What we can do now, if we have access to the receiver, which Timo just saw, so to the transmitter actually, that side. So we perform the power analysis attack using the scope. We did this back in Bochum, so we will not make a live demo of that here. But basically we were able to recover the device key of this.
So it's the device key of exactly this transmitter that is already known to this receiver. Right? So we can now show whether we are able to clone it by just putting the device key in the appropriate field.
And we try the decryption again.
Hooray!
So in the first two messages we intercepted were actually two consecutive messages, and you see that the counter value was just increased by 1. Maybe you sent one other message just to show that the counter value...
And to see that the program is still working. No?
Yeah. Another one.
Oh.
Press decrypt again, and now you see the counter value is being increased, C2, C3, C4.
And in decimal, you can see the counter value. So this is the current counter value that is in the receiver, and yeah, that is currently also in the transmitter.
And we said we are now able to clone the device, so actually the PC should be able to send the message, and
Yeah,
as you see...
I might just hold this. We are not cheating. I'm not using this, so...
It's working.
only the-
Nice. Just for the fun, I sent another one. All right.
It's very impressive, but how practical is this, or what can you do with this?
Yeah, it's a little bit, well, one question?
If you now use your remote, it should work, right? Because the counter is increased.
Oh,
Yes, this
someone,
was a very good question.
yeah, it's right, press it.
He said if we now press this remote control, it should not work because now this counter is old compared to the one in the receiver, and we try this, nothing happens. And it shouldn't even work for a second time because we open the garage a second time, nothing happens. Now the third time, it should blink again.
Yeah.
Very good question here. You win the prize.
Wow. Okay. The other question?
Or maybe because there's quite a lot of questions, so maybe we can postpone this to the end. It's not so far away, then we can answer all the questions at the end. Otherwise, we run completely out of the time, probably.
Yeah, so what are the implications? Well, some people might now, maybe that was the next question, might now say, if I have the remote, why don't I just take the car? Or if I have the key, why don't I take the car and drive away? Well, of course, you can do that, but there are some scenarios where this attack might be interesting.
Yeah, the problem is you need physical access to this, and there's no, we thought weeks and weeks, what can we do with this? We've got this attack that we don't know what we can practically do.
Yeah, and actually what we can do is, for example, we rent a very expensive car, we clone the key, and then we can return the car legally, and we can get access to that car at all times. Similar scenario is if you give your key to some, I don't know, cleaning personnel in your house, they'll have access to the key for a while and return it, and then this of course only makes sense for very high value targets.
Yeah, you
right?
must have a lot of money in your car, so that to perform a sidechain attack just to clone this key. I mean, there's easier things to just throw in the window or whatever than cloning this key. So this was just a demonstration of how the attack on this transmitter works.
Yeah, so what happens if we do the same thing to the receiver? So now we get the manufacturer key. This alone is not yet scary for the owner of the garage, but it might be more scary for the manufacturer of the garage, because up to now he was the only one who was able to produce valid or operating remote controls. Someone who owns a manufacturer key can also do that. And now it's getting more interesting. Once the manufacturer key is known, we have a completely new scenario.
Now all the people who are already sleeping here can wake up, because now I come to the
Interesting.
important bit.
And basically we are back to the scenario from the first slides. We have the transmitter that sends a keylock encrypted counter message to unlock some device, and we again have some eavesdropper, but this eavesdropper now knows the manufacturer key. So what can he do? Well, actually, he's able to, after eavesdropping some communications, he's actually still able to clone the remote.
Yeah, it's very similar to the fixed race. I think this is worth demonstrating, Thomas. You are the victim.
No, not again.
Well, we always need, if we want to demonstrate it, we need two people, obviously. Thomas is the victim.
No, I'll do the attacker this time.
Okay, I'll be the victim. I'm the victim. I'm, of course, very rich. And I live in my big villa, and I've got at least 2 garages and a lot of luxury cars in the garages. And, of course, I live in the USA. My garage is connected to my house. And for Christmas, someone gave me as a present this highly secure keylock remote control that now allows me to very comfortably open my garage with a remote control. Yes, that's me, victim.
Yeah, and well, I'm his neighbor. I was always wondering what he's storing in his garage. And actually, I attended the Chaos Communication Congress in Berlin in 2008, and there was this interesting talk about opening garage doors, and actually I listened. So now I'm waiting in front of his house and waiting for him to leave his house and his garage and to send some messages I can record.
Yes, and I get up early in the morning, as usual, 11:30, and I have my breakfast, and before going to the beach, I open my garage, and then I go into my car and take my surfboard, and then I drive away with the car. Brum, 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 brum. Of course, I do not forget to lock the garage. It's locked again, and I'm off to the beach, right? I'm gone, very far away.
So now I have the manufacturer key, and because the serial number was transmitted in plain text, I also have the serial number, which we can already see here. And for the key derivation, all I have to know is those two things, the manufacturer key and the serial number. And so now I'm sitting in my car and can do my own key derivation. I end up with the key. I can decrypt the message to get the counter value. And then I just open the garage. I enter the garage, I get all my tools back, which I borrowed to my neighbor over the last years. And of course, then I leave the garage again, and I'll close it after I leave.
Yes, and I come after a nice day on the beach, I come back home, come with my car, I try to open the garage. You already notice it, nothing happens, but I'm used to it. These modern systems are not very reliable. I press another time and the door opens. I park my car and I know suddenly I look around, something's different. Where are all the tools that I took away from Thomas? Thus, I notice now I'm in a very difficult situation because I always had this transmitter in my pocket, so no one can have access to my garage. It's a highly secure keylog system. And there are no, if he was a little bit clever, there are no fingerprints and there's no proof. How can I tell my insurance now that he had been into my garage or house? So I'm not really happy about this. Hate you.
Hey.
Yeah.
We're all friends.
Yeah.
Yeah, and what you just saw, it works for all key derivation schemes we are aware of. And it works instantly, as we just presented it in all cases where the serial number is used in the key derivation. If there's a seed used, we need some calculation time with the PC to recover the seed. And if it's a very long seed, we might even need some special crypto hardware like the Copacabana, which was also developed at our chair.
Yeah.
So, just to explain it.
We quickly have a look again what happened here during this attack. Why did it work so quickly? What went on? So we eavesdropped. One is sufficient on one of the hopping codes. So we had the serial number. We have the input to this. We also have the manufacturer key, either because of a sidechain attack or from somewhere else, social engineering. So we can at once calculate the device key. And if we have the device key, Thomas intercepted one hopping code. So he knows the current counter value in the receiver, decrypt the roaring code, generate the next valid counter, and open the garage. Important to mention that this extraction of the manufacturer key just has to be done once for every manufacturer, right? So knowing the manufacturer key of one manufacturer lets you perform this attack on all of his systems. And of course, even if you cannot do the side-channel attack on your own, you might either ask some criminal cryptographer, or we don't know, maybe after the 2025C3, there's a long list with all the manufacturer keys on the internet, wherever you get it from. The problem is with the knowledge of this key, the whole security of the whole system falls. And that's the big flaw. Yeah, we can even go one step further. There's one question here.
Is there any protection if a brute force attack for the counter can send constantly the messages?
The question was if we could perform a brute force attack on this counter, and the answer is yes, and we come back to this at the end of the talk. Okay? There's another slide for this. So we can go one step further and take over the whole keylog system. And for this we need to have a closer look at this counter again. In theory it could be unlimited, but in practice usually you have like 16-bit, say 16 bits, 65,000 values, and then you start again from value 2, so you can draw it like a circle. The green dot indicates the current counter in the remote control, and the red dot the one in the receiver. And now maybe it might happen that, for example, your daughter, she plays with this remote control. What happens is that the counter in the remote control is a little bit ahead of the counter in the receiver. So now if you press 2 times on the remote control, the value in the receiver will resynchronize to the value in the counter. Okay? So this is also what we saw why I had to press 2 times. Resynchronizes to this, and now usually when we press on the remote control, the counter is increased by 1. Now with this software and the expensive equipment from the hardware store, we can of course generate any valid counter. So let's just produce this counter value here. What would happen is that the original remote of the original owner is the beginning of this block window. And this means for the owner, for the original remote, that he has to press like 30,000 times now to open his garage. We can also quickly demonstrate this, of course. So maybe, Thomas, you are the victim this time, no? Can you where's this? Here.
Yeah, I think you have it here.
My pocket. So we intercept the last value so to make it more accurate. So the last value was 747, like Cologne. And we rise the counter now by 5, so we have 5 to and send the new value. Now the receiver is approximately 5 times ahead. And
I have to press a couple of times.
Yeah.
Press
1,
1,
2,
2, 3.
4. Ah, it's opening. Okay. So we already saw this, and now we just rise this value by, say, 5,000. 5,000. 1. Oh, nothing is happening. This is not good. You can imagine what would happen. Oh, it's going on. Something is going on. I had to press twice because to start the resynchronization of the receiver. So now Thomas can press very, very often. Maybe you give it to someone in the audience.
Who wants to press?
You win a prize. You win a prize. If you succeed
Right.
in opening this door, you win a prize until the end of the talk. So we have to hurry up. We have to speed up now.
Good motivation, yeah.
Back to the talk. So, yes. Now, of course,
It's working
you
hard.
are pressing there. Of course, we can still open the garage, no problem. You can press as much as you like. We just click on the button and it's still open. You can press as often as you like. No chance for you. So, that was the practical part. And we're getting very, very close to the very, very end of the talk.
Yeah, so let's start with the summary. So what you saw is that, what we showed is that security only by obscurity makes insecure system. The cipher was kept secret, and shortly after it came out, or also other groups were able to break this. So do not rely on obscurity for security.
Yeah, you see this, what Carsten and Starbuck did, the reverse engineering stuff in the morning. You saw all the fuss about other ciphers, other weak ciphers that were kept secret, and one day the crypto community knows about the ciphers, they are broken very quickly. It always explodes if you just try to produce the security only by obscurity. Obscurity can be a good additional ingredient for good security, no problem. Yeah, we also showed that DPA works for commercial access control systems. Hopefully everyone has seen that this works.
And we also showed, hopefully, that some of the severe attacks can also be done by non-specialists. So not everybody needs to have an expensive scope at home to perform this attack and has to have security training at the Ruhr University Bochum or something like that.
Yeah, we've got a very good, you can study IT security in Bochum, of course. I can recommend this to everyone. You study IT security and then you know what real security is. Cyber attacks are a real threat for all unprotected implementations of cryptography. This includes everything. The AES, Advanced Encryption Standard, is being used by the NSA for top secret messages. If you implement it without any side channel resistance, it's very straightforward and very easy to break it, even the mathematically very secure ciphers. So also in the case of Keylog, it's not the weak cipher that made this attack possible, but it's the fact that it's implemented in a non-side channel resistant way. And yes, all the floors with the key management, of course.
And what's also true is that although side channel attacks have been known for about 10 years now, most of the embedded systems you will find on the market still don't have any protections against side channel attacks. And yeah, well.
And it's really laugh because we saw it's not a very new thing. It's known for a very long time already. The side channel attacks. Yeah. We're getting in trouble at the time. Disclaimer, our attacks do not imply that real-world systems have actually been attacked by SCA by criminals, merely by researchers. And we've got some literature here. The first is we published this attack on the crypto conference. You see, we do not only like long titles, but also long lists of authors. And one of the authors is also worth mentioning here on the 25C3. It's Amir Moradi. He should be a member of our group in Bochum. And he applied for a visa several years ago. Several months ago. But there is one problem because he's from Iran and he is working on security topics. So he's still waiting for his visa. Very bright researcher, and he helped us a lot with this. And we are very unhappy that the state does not allow him to work with us. It's a shame.
Not yet. We hope this will change next year. Yeah.
Yeah, then we have the mathematical papers here, Andrei Bogdanov, and then the proof and text by Courtois and Sebastian Indestege. Thomas, I've got this highly secure keylog system now in my car. Do you have any recommendation what I can do now?
Well, of course, this question came several times. And actually, when I was walking through the street a few weeks ago, I saw a quite good solution, I think. Maybe you also want to try that for your car. Well...
Okay, first show the picture.
Huh?
You can show the picture first. Yeah, this is the solution. Yeah, we skipped the advertisement because we want to mention two important conferences. One is the chess conference, takes place next year, 2009, 6th to 9th September in Switzerland. The chess, cryptographic hardware and embedded systems was founded by our boss, Professor Christoph Parr, and he's now, the conference is now the most important conference for all things concerning side channel attack and implementations in hardware. So everyone who's interested in the topic in general should definitely go there.
And the other one we want to advertise for is Eurocrypt, which will be held in Cologne next year, in April. And it's one of the biggest crypto conferences, and it's organized by the HGI, which we are also part of. It's a crypto group in Bochum, basically.
We are very proud that this takes place in Germany, this conference.
All right.
And to answer the very first question about brute forcing the seed space, when you use a random seed for the key derivation of the serial, it has something to do with a cost-optimized parallel code breaker. And we looked a long time for a name, and one colleague said Copacabana. We said, yes, Copacabana is a very good name for it. It's 120 FPGAs operating in parallel. The result looks like this, and it can break a lot of problems. It can break the DES in 6.4 days on average. It can break the A51 that is used for GSM communication, electronic passports, so it can track identities, steal identities, track people, and we can break keylog. And here's the numbers. This is just a very straightforward implementation, just to have some numbers, how long it would take. The 32-bit seed is used, one FPGA, 39 seconds, okay, that's real time. For an 48-bit seed, it takes 6 hours in one Copacabana, and now if ever the 60-bit seed would be used, it would be secure to brute force. The only problem with this is that we never saw a system in practice where the seed is used. And of course, after our attacks, we had a lot of new friends and manufacturers came and talked with us, and we asked them, why don't you use this seed? And the very interesting answer is that it's too complicated for the customer to have a separate button for sending the seed in the remote control. That's the reason why these systems are not used in the field. The reason is that the customer is not able to enter the second button for the seeds.
Yeah, customer acceptance factor, yeah.
Okay, now we are ready for more questions. I think there were some more questions somewhere.
There was something about the brute force.
Will you be running around with the microphone, no?
I would ask you to just repeat the question, so I don't have to run around here.
Shout and I will repeat the question. Mia, the question was if we have ever worked with one of the garage doors where you put in a birthday, whatever, with 4 codes, for example. The answer is yes. This was at the very beginning of the talk. You are talking about a fixed code system. A fixed code system always transmits the same code to open the door. So it's very easy to eavesdrop on this and to replay this code. There's no security, probably no security in your garage door.
Yeah. So basically all you need is this equipment and do not need to do any security stuff. Because you have to differentiate. So usually you will send the serial number and the counter value encrypted. That's your normal message containing the counter value. And the seed you would just transmit during learning mode. So that's a different message. So could send both messages, but then the seed doesn't make sense anymore because the attacker also knows the key, the seed. Sorry. Yeah, your question, we forgot you.
Are there two or more keys called keylock systems? For example, I have one in my car and one with my girlfriend or whatever.
The question was if there are 2 or more keys in a keylock system. For example, one to open your car and one to open your garage. Is that correct? For opening your girlfriend.
Ah.
No, what it is, I understood the question. I think it's you can have these separate remote controls, but they can all rely on the same manufacturer key, but will have individual device keys. But all the individual device keys will be derived from the big master key. So it will still be the same problem that once you know the master key, that you can probably derive the device keys for the separate remote controls.
The question ends on the counter system.
Yes?
If you have 2 keys or more keys, you should have more counter systems.
Yes, you were asking about this eavesdropping attack, right? With the counter.
Actually, the receiver, once, so in the learning mode, you take a new transmitter, you press one button here, then the receiver is in learning mode, then you press the transmitter sends the serial number and the counter value, and the receiver will store both values. So the receiver has a list for the different keys or transmitters that are registered, sorted by the serial number, and for each serial number there's also a counter value stored. So basically the receiver can, or the garage door can even distinguish between your key and the key of your girlfriend. They're different.
And of course your girlfriend would still be able to open the garage. So in this case we would only take over control of the one remote and the one of your girlfriend would still work. By the way, now it's past 12. I want to say happy birthday to Dario Carluccio, who is his birthday today. He's a very important cryptographer. Okay.
Where do you see implementations of these systems? Is it only garage doors, or do you see those in car doors, or where else do you see those?
So what it is, as Thomas already said, 99% of the garage, if you have a garage door system that uses a changing code, it's 99% it's keylock. And it's also used in some cars, but usually you are safe as a car owner because usually these systems are used for opening the cars. Usually you have, in addition to this car, immobilizer, which typically does not rely on keylock but on some other system. We saw, what concerns me is there's a lot of alarm things, like car alarms and stuff like this, that is also based on this. So you should be careful what you buy. You might just ask what cipher is contained in there. No one will tell you, of course.
Well, actually, many people advertise with keylock because, well, it's securer than the password-based system where you always send the same code.
It's interesting that you can still buy these systems. So just last week I did some looked on the internet and I saw, yes, you can still buy these systems and they are just advertised as usual and they are highly secure and everyone is happy. It's surprising for me that, yeah, you are just the customers, no?
To develop systems like that, isn't it? So, people are reluctant. presumably people are reluctant to change these systems because they're quite expensive to develop. So it's cheaper to claim that their systems are secure rather than, developing a new one, I suppose.
They are already in the field. It's difficult to change systems. There's another question right far at the back here. You need to shout. The question was what frequency is used, and the answer is usually for these rolling code systems, frequencies in the so-called ISM bands are used. That's 433 megahertz or 868 megahertz, with 868 megahertz being the better option for those systems because on this frequency you may not transmit for a long period, but only for short. The duration of each transmission is restricted so that your system might operate more reliable on 868 megahertz. So that's the most common two frequencies. Very old fixed base systems, they operate on 40 megahertz and other lots of frequencies, but typically 433, 868.
Have you been approached by insurance companies for advice about risk assessment?
The question was if we have been asked by insurance companies about our findings.
Well, I think for sure we have been asked by people who had trouble with the insurance company or something like that. We have had letters from private persons, even being in some kind of lawsuit or something.
Yeah, but there were also insurance. I remember that there was some insurance coming with car keys, and we looked whether there was keylog in there and stuff. Because yes, for insurances it's highly interesting because they've got a lot of cases where stuff is stolen and they have no explanation how this stuff vanished. And yes, they come up with these cases and ask whether we can help them. But usually we cannot help them because yeah, there's no evidence. Any more questions? Over there, please. Yeah, so this was not a question but a remark that one could find out that if a receiver has been manipulated because one could find out if the block window had been shifted. But as you saw for this eavesdropping attack, it's only shifted by one. So if Thomas did not close the garage after I went to the beach, the counter in the receiver would be only one value ahead, and this is difficult to prove. One value ahead. So.
Yeah, usually if your garage doesn't open, what do? You just press another time. So then the evidence is gone.
Do you have any more questions?
What happens if you set the counter to the maximum value? Is it locked forever?
What happens if we set the counter to the maximum value? No, because maximum value, it just turns over. So after 1 comes the value 0, 0, 0, 0. That's why this block window is always moving.
You set the 0 because that will be the log of the next number, and then the device checks, is the number I get, is it larger than the one I got? But it's not because it's 0.
It checks whether, so the receiver is there where the red dot is. And all values before this means all values, no matter if we cross this place where 0, 0, 0 changes to 1, 1, 1, all 30,000 values ahead of this currently stored value are the block window.
If we're really in a circle, the word before does not make sense.
You were saying if we are really in a circle, we what?
The word before does not make sense.
Yes, the word before does not make sense. I could explain it mathematically. If we are calculating here modulo 2 to the 16, then we could just subtract and we would still remain in the space, in the number space up to 65,000. This was no good explanation. As usual, mathematical explanations are never good. I will explain it to you personally. Okay. One more question in the very back. I can hear nothing, sorry. Oh, you want to try to explain it? Maybe the three of us sit together and we explain it. Okay? Are there any more questions? So may I ask a question? Who of you has got such a remote control garage or car alarms? No one? 1, 2, 3, 4. So, yeah, maybe. Okay. There are quite a few. Okay.
Is there a list available with pictures of remote controls?
Is there a list available with pictures of remote controls that use keylog? No, but if you want, you can start it. I don't know so much about this hacker paragraph thing. You might take this into account then when you publicize this list.
But if you want to find out, you take a look at your transmitter, and if there's some kind of dip shelter, dip switch, yeah, it's not really big. Inside, then it's probably a fixed code system. If it just has buttons like this one, it's most probably a keylog system.
One more question over there? Sorry, I did not get this question, so maybe I will quickly run over with the microphone and then you can repeat it. English?
Okay, when you receive the signal, how get you the ones and zeros for the PC out of the signal that is transceived over the air?
Okay.
That's actually why we got this stuff from the hardware store and connected it to the PC. Basically, there's this RF part inside of the receiver, and we're just picking up the signal right behind the RF part of the receiver. So there's, radio part. It transforms the message or the signal sent via the RF interface into an baseband signal, into zeros and ones. And we just put them into the PC via the
It's no secret. If you want to learn it, you look into the data sheet of these HCS chips by Microchip, and there they exactly explain you this Manchester encoding that is used for the transmission, and they exactly explain how to, there's even source code for this available and freely available data sheets by Microchip that explain you how to get these hopping codes out of the field. In software.
And we just were too lazy to build it ourselves, so we bought it from the hardware store.
We come back to you later. You're sitting too far in the back. One more question here in the front. Does that mean we are bit banging with the parallel port? Yes, we are. We just use one output pin and one input pin. This acknowledge pin of the parallel port for the input. We just all the time bit banging. It's called. Yeah, at the speed of Windows, which sometimes makes it more difficult. That's why the folder on the desktop is called live demo. That usually works.
Usually, yeah.
Usually works.
You were quite lucky.
It has something to do with the Windows, magic Windows timing. And parallel port is always difficult with the bit banging. Yes. Another question. No, we won't show you the manufacturer code. Unless you pay, maybe after, if you've got 1-2 millions, we can have a personal talk after the presentation. We might find a criminal cryptographer for you somewhere. Iran.
On which day will the workshop be?
It will probably start tomorrow. The problem is, as usual, we are a little bit late with our planning. So we've brought all the equipment, we have got it running, but it will, during the day tomorrow, we will put some traces there and we will put some information where you can meet us, because it's rather complicated. We are a little bit late to find a place where we can put our equipment. Works the room? I know that it's there, but we did not find yet a quarter of a table for our scope, but we will sort it. Yeah.
We did, and they probably answered already, but we didn't check the emails the last few hours.
On the wiki site, you will find more information tomorrow. So we will definitely find the time tomorrow to acquire some traces and put them there, and then we will put some time slots where you can meet us personally so that we can help you with your attacks to get them running. Maybe we can even make a competition, who is the Hall of Fame, who is the first to break the stuff,
nice.
we will see.
And if it's not going fast enough, just write an email, right? You will find our email addresses written in the wiki too.
Somewhere
So,
maybe somewhere.
How much does the near field probe cost? How much does that near field probe cost?
The near field probe.
wasn't so cheap.
No, it was no.
Do you remember the price?
No, 100, 200. I would guess like 200 euro. Near field probe. It depends. We've got a
That's
full
important.
set with this preamplifier and so on. And because it's highly sophisticated measurement equipment, it was not like 20 euro, but in the range.
You can also try to do your own coils
Yeah,
and
it also
use
works.
them. Yeah.
But this preamplifier is quite good because it is a low noise floor.
Yeah.
So, more questions? So,
Right.
if there's no more questions, we say thank you for your attention and it was a pleasure to come to Berlin.
Verbeuden so much.
I'm impressed. I guess. Oh. I guess someone earned a beer or two, right?
This is the, what is your name?
Tora.
So this is the guy who succeeded in pressing the remote until the end of the talk, and of course you will get some prize. We need to share some there. Thank you so much.